Hey everyone and welcome back to PrepFusion. Okay, so I'm sorry that I have to extend another lecture because in the previous lecture the time was spent with the solving the questions only, and the summary I know will go a bit long because I have to cover a lot of things. So that's why this is another lecture. In this lecture basically I will just cover the summary and give you a brief overview of the state space, right? So this is basically the summary, right? So summary, I have written few things down, okay, to explain them further, few topics, okay. So like the first thing is like in the previous lectures I may have messed up a bit of the question numbering. That doesn't matter to you, okay, but I have corrected those question numbers. And in few areas, right, in notes while speaking I was speaking something else, or maybe I was writing something else there. So I have also made few corrections there, one or two corrections, okay. So in one case I was like finding the output, okay, and there was like it was a like a two row matrix, and I have written only y of t. That y of t means a column matrix with y1 of t and y2 of t, okay. So yeah, it may would have happened. So if any doubt comes, right, you can always text me in Telegram or something. We can always clear the doubts, right? So yeah, here I will explain it to you that which things are important and not important, and which things you should keep in mind, right? Okay, so first thing is like from where did we start? We started from state variable, right? So what is state variable? Tell me, okay, what is state variable? State variable is the variable that is responsible for changing the state of the system. So what does variable mean? Means change, right? It varies. And state means state, basically, okay. What is the state of the system, basically? Okay, state means state. So the variable that is responsible for changing the state of the system is known as state variable, right? Now what is state equation? State equation is basically a first order differential equation that is used to express the state variables, right? With with the change in the state variable that is used to express the change in the state variable in relation with the input and the state variable itself, right? Okay, so that is basically state equation. So state equation, okay, state equation is a function of x dot of t, function of state variable themselves and the input, okay, and the input. As state variable, the variable those that are responsible for changing the state of the system, responsible okay. So these are two things. Now state diagram, basically a pictorial representation of the state equation or the state space representation, right? State space representation. State space representation means it involves both the state equation and the output equation, right? So what is state diagram? Basically state diagram, right, is a pictorial representation of state representation, right? Basically state space representation, basically state equation and the output equation, right? Okay, state equation and the output equation. So these are the three things that we learned in the first lecture, right? I hope you remember. Then basically we learned about how to convert my like equation, like differential equation, into state equation, right? So basically, right, I have been given a differential equation, okay, second order, third order, whatever differential equation I've been given, okay, higher order differential equation. I have to convert that into first order differential equation and then into state equation, okay. So what I did was, firstly I converted it to first order differential equation. How? We solved using the controllable canonical form, right? During the first few lectures I didn't tell you the name, but we solved using the controllable canonical form. So we converted them into first order differential equation with the help of CCF, right? CCF, okay. In CCF, what we used to do, we used to name the first state variable, okay, which will be equals to y of t, okay. I mean it can be related like this one, that my y of t will be equals to x1, okay, then my x2 equals to x1 dot, then the other one will be equals to that, and the last state variable, right, last state variable, okay. Basically if the order like this order is 2, then there is fine. If the order is n, we go n. If the last state variable will be some function of all the state variables and the input, right? Okay, it will be function of all the state variables and the input. So yeah, this is how we used to solve using controllable canonical form, CCF basically. So yeah, this is how we used to convert the differential equation into the state equation. So next, what we used to do was convert the state equation to the state variable, state diagram basically. Okay, we have the state equation. Now we want to show it pictorially. Okay, so what we used to do was write the cause effect relation. This we have done multiple times in SFG also. Okay, cause effect relation. Then from there, writing the cause effect relation, then we drawn the SFG, right? Drawn the SFG by the cause effect relation. Like first convert into Laplace domain basically. Okay, convert to Laplace. Okay, then we wrote the cause effect relation, and then we drawn the state space diagram for each of the state variables, right? So yeah, this was this one. So how we used to do? So basically, right, if let's say I have a state variable here, okay, this is x and this is x1 dot, okay, and this is, let's say, 1 by s. So one more thing I have to do is take care of the initial conditions. So the initial conditions will lie just above the state variable, right? x1 of 0 above s. Okay, just go back to the notes, right? Just go back to the notes. You will see that my initial conditions will lie just like above the state variable. Okay, so yeah, this was that because what was the reason? Because if I take that Laplace inverse, right, Laplace inverse of Laplace of s differentiation, then I will get an initial condition term also, and that will get added with this one. Okay, so this one gain will be 1. Okay, this was one of the basic SFG that we taught in the first lecture, right? So I have to write initial conditions will lie above state variable. Okay, so next what we do understood was, okay, one more thing I forgot, that here, right, the number of integrators will be the order of the system, okay, or number of 1 by s terms basically. Like this thing you have to remember, number of, in the state space diagram, right, number of integrators will be equals to number of 1 by s terms will be equals to order of system basically. Okay, so yeah, these are the few things that we have to keep in mind. So what was the next thing that we did? The next thing that we did was basically the difference between natural response and the forced response, right? So what is natural response? Remember, natural, what does natural mean? Natural means it is naturally present in the system. Okay, so this p has been missed somehow. Okay, I don't know why. Okay, so it is something present naturally in the system, so I'm not forcing anything. Okay, I'm not forcing anything. So what is it? Through input I force some output, right? But natural response is the basically the state response. Okay, or we can say zero input response. Input is 0 at that case. So natural response means 0 input response. And what does forced response means? I'm forcing something, I'm forcing an input, so it is 0 state response. So state is not there. Okay, it is not naturally coming, so I'm forcing some input. So like this response will be my some function of state variable, and this response will be some function of state variable, and this response will be some function of my input, right? So function of x, function of input. Okay, now again, right, this state space representation, what is this? So I will write the representation here in a good manner, okay, so that we can revise, right? We can revise. So what was the representation? So simply you might say that this x dot equals to ax plus bu, y equals to cx plus du. You might say this is a representation. No, you are forgetting one thing. You are forgetting the orders, and this is a matrix format, right? So I have to write the orders and write in matrix format so that you can recall, right? So what is the matrix format? So matrix format, right? So in matrix format I have to write orders of each of them. So let's say my order of the system like is n. So what will be the order of this x vector? Okay, basically the differentiation state vector. What will be the order of this one? This is a, what is this? Is this a column matrix or a row matrix? This is a column matrix, right? So my number of column will be 1, but number of rows will be n, right? So n cross 1. Okay, and what is a? A is n cross n. A's order is n cross n, right? We remember that. Now what will be order of x? So x is also a column matrix, right? So x order will be, what will be the order? It will be n cross 1, right? So okay, and what will be order of b? Order of b. Okay, so okay, let me write the definitions of n, m, and so n, what is n? So n is the order of the system, right? N is the order. Okay, order of system. Now what is m? I hope you remember, right? What is m? M was the number of input that I'm given to the system, right? So m was the number of input. And what is p, right? P is the number of output, right? Number of output that I'm giving to like taking out from the system, right? Number of outputs. So the, what will the order of b? Order of b will be basically n cross m. Why? Because my number of rows has been fixed by this, but my number of columns will be fixed by this u, right? So it will be n cross m. And this is what is this? Is also a column matrix. Basically this is m cross 1, right? And what is this one? So this one, right? This is also a like this y is a again column matrix. So all of them, like these are vectors, right? These are vectors. This x y, this x, this u are vectors. These are matrices. Okay, they are just nomenclature, don't worry. Okay, you just understand that this is a column matrix and that is a row matrix. I mean that is normal matrix, rectangular. So this is p cross 1. Okay, and this c, right? What is the order of the c? C is p cross n. Okay, because x has n cross 1 order, right? X has n cross 1 order. So what is basically D matrix? D matrix is basically it is a relation between the input and output. So its order will be P cross M. So it is relation between the output and input. That's why the order is P cross M. Okay. So from here you can understand the row is fixed, right? Row will be P only because row has been fixed by this one. Okay. Now what I need to think? I need to think about this one. Okay, the column. So column will be decided by this one. Column will be decided by the rows of this one. So what are the rows of this one? It is m cross 1. So yeah, this will be m cross 1. Okay, we have already like learned this. I'm just summarizing you, okay, in a like very short span of time. So one more thing, I told you one more thing, that this whole thing is known as state space representation. But this equation, right? Okay, let me make this a bit more smaller actually and take this here. Okay, what here? Okay, this equation is known as the state equation and this equation is known as the output equation. Okay, okay, so I hope you remember all these things. Now like I will define like each of them. So this is like, I'll just tell in brief. This is the state vector. Okay, this is a column vector. This is the system matrix. This is this is the differentiation state vector. This is a system matrix. This is the state vector itself. Okay, and this system matrix, right, this has some properties. With the help of this system matrix I can find the eigenvalues, and with the help of eigenvalues I can find the poles of the system. Okay, and if I can know from knowing the location of the poles, is the system stable or not. So about stability, right, about stability we'll go into the next topic, time response. There we'll understand stability a bit more. In basics also, I think I gave you a brief overview of the stability. So pole lying on the left hand side will make the system stable, pole lying on the right hand side will make the system unstable. In state space also I maybe have done few examples of that, right? So yeah, so with A matrix, very important, with A matrix I can tell the location of poles, right? So yeah, the A matrix is important. This is basically state vector, so it is collection of state variables. This is a differentiation state vector, okay, and this is the input vector. I already told you this is the input matrix basically, okay, and this is the output vector, this is the output matrix, okay. This is the basically again state vector, this is the transmission matrix, and this is the what do you call input matrix again, okay, we already know. So this is known as the data transmission matrix basically, okay. So yeah, all the orders and all those things have been written. So next what we did, next we did was the state space diagram to state space representation, okay. We are going the reverse direction now. We had the state space representation, okay, here like the differential equation you're talking. So state equation we had, we went to state diagram, okay. Also output equation we had also, okay. Then only we can go state equation and the output equation. Okay, so yeah, now right now like that there was some procedure there, we wrote the cause effect relation and all those things. What is the procedure here? Remember, right? What was the first step? First step was to write time domain expression. No, right, delete the integrator, those integrations, delete those in the SFG. No, it was to remove the initial values. So if there is some initial values, right? So first step was remove initial values, because in representation the initial values doesn't come, right? Okay, remove the initial values. Then what was the next step? Next step, as like many of you thought, write the time domain expression, okay. This one was 1, this one was 2, expression. Then what was, then remove the integrators, right? We have to remove the integrators. Remove the integrators, right? So basically that what we should do. But one thing we have to keep in mind in this case, right, going from state diagram to state space representation, was that if there is some multiple forward paths to the same state variable, or there is some loop in the state variable present, okay, then we have to solve it caution, and we have to use the principle of superposition, right? So if there are multiple forward paths, right, from state variable, then you have to use the principle of superposition, okay, and solve for each state variable, right? Okay, so basically, like, let's say I have this x1 x2 and there are multiple forward paths, right? Then we use the principle of superposition to solve for, let's say I will solve for, let me write here, I will solve for x2 dot by x1 first, okay, making x2 equals to 0 and u equals to 0, let's say, okay. Then x2 dot by x2, making the other two 0, and like that, okay. So yeah, this is how I get each of the transfer functions, then I add all of them, then I get the state space equation for x2 dot. Now I have to do the same thing for x1 dot, right? So I'm just basically revising you, okay. So what we did also, right, so while drawing the state space diagram, one thing also what we did was that like my state variables, right, state variables will be present just before and after this one by integrator, right? I mean, this will be the differentiation state variable and this will be the normal state variable. So just after the 1 by s, okay, I will write my state variable, okay, not just anywhere else and not just any place, right? I will write my state variable just after this integrated, okay. So yeah, that is important, like the conventions, all those things are important. So next we studied like basically eigenvalues and eigenvectors, right? So first topic was first thing was their transformation, right? So transformation means I'm changing from one basic axis, okay, to another, right, another axis, basically from one basis to another basis, or you can say from one axis to another axis. Now why is this important? I told there also, like let's say you are in a jet plane, right? You are in a jet plane, you're going like this straight, but what happened, your plane turned like this one. Now you have to drop a bomb at this point, right, at just the bottom. But if you would have dropped it like this, then the outcome would have been different. If you would have dropped it like this, then the outcome will be different, right? It will drop something like this. Now I have to transform such that I drop here, right? So I have to do some matrix multiplication. So all those things, right, transformation helps us to understand, right? Next we study basically span. Okay, basically span. So like span, right, span is the combination of vectors. Okay, two different vectors I will be given, let's say a and b, one is I minus j, one is I plus j. With the combination, different linear combination of those vectors, how much area can I cover, how many dimensions can I cover? Okay, that was basically span. So transformation is used to change the basis. Okay, change the basis, right? Now what is next? Next is span, right? Next is span. So span means how many dimensions I will be able to cover with the linear combination of the given vectors. Okay, how many, basically let's say for a 2D, right, if I am able to cover particular area, particular two dimensional space, I will say that my span is 2D. So with let's say ij, I plus j and I minus j, right, I'll be able to cover all of the 2D plane, right? Then my span will be 2D only, two dimension, right? That is the main definition of span. So how many with linear combination of vectors, right? Okay, so that is basically span. So it can be 2D, 3D, anything. Now rank, right, rank is equivalent to span only. Okay, rank tells about the span of a vector, right? It's equivalent to span only. So if like I can cover 2D, then it will tell me the rank is 2. If I can cover like 3D, it will rank will tell me I can cover a span of 3. So that was rank, and rank is very important. Rank is very important, right? So rank tells that how many columns or rows are independent, right, in that matrix. Okay, that is also like what rank tells. Rank tells us the minimum number of independent rows or columns. Okay, that is also definition of rank. All these things we'll study in matrices also, don't worry. So this we studied. Next one was very important. Next one was the scaling equation. Basically scaling equation. What was my scaling equation? So scaling equation, right, scaling equation basically is the eigenvector relation, right? So if I have a matrix A and I want to transform it with the eigenvector V, but what I see is it's in the same dimension as the previous one, right? It doesn't transform. So let's say first my vector V was here, right? Vector V was here. Okay, then I transform it with like multiplying with this one, right? A, right? Multiplying with A, I try to transform this matrix. But what happens is that still I'm on the same line, right? Along the same line or same dimension. Okay, it is just scaled by lambda. Okay, so this result will be lambda V. Now this is known as the scaling equation. Okay, my direction doesn't change. Okay, I'm in the same direction. So this is known as the eigenvalue. Okay, this is known as the eigenvalue, and this is known as the eigenvector. This is known as the eigenvector, right? So yeah, and like also this eigenvalue, right, this eigenvalue is also known as the scaling factor. Scaling factor. Okay, so yeah, now how do I find this eigenvalue? I hope you remember, right? What we should do was we used to vary this eigenvalue, and for that particular eigenvalue I used to find satisfy the equation. What was that equation? Basically I took this here on this side, so my equation becomes like something like this. So this is a v minus lambda v equals to 0. So a minus lambda times v vector equals to 0, right? Null vector basically. Okay, so what I will do, I will, sorry, there is lambda I also, not just simple lambda, there is lambda I also. Okay, so I'll delete this one. So this one, right? So what I will do, I will vary this lambda. Okay, and for some lambda my equation will get satisfied, that a minus lambda I multiplied with this v vector will give me null matrix, right? So null vector, or you can say. So that is what I will do. Okay, after finding the lambda, what I will do, I'll put it back into the characteristics equation, which is this one. This one, right? Sorry, like this one I will vary, but obviously, right, I can just simply find this value. What I will do, I'll find the value of lambda. Okay, simply just varying lambda will not have, I will have to vary so many values, but there is one method to find this. So what was the method? Method was simply this characteristics equation, which was a minus lambda I, like determinant of a minus lambda I equals to 0, right? So from here we'll find the value of lambdas. Okay, find lambda and then put this value of lambda back into this equation. Okay, or like into this equation, put value of lambda into this equation. A v and this is lambda v, right? This is lambda v. So yeah, put this value of lambda in this equation back, right? Then I will find my eigenvectors from this equation. Okay, find my eigenvectors. So this is how like the process goes on. First I find the value of lambda with the characteristics equation. So this is known as the, I will write in short, characteristics equation. And then after this one, right, I will go to here, or like if I found lambda, then I will put this here and I will find the relation between a v and the lambda v. Okay, so yeah, this is what I will do. So one more thing was that basically that this Cramer's rule, right? Cramer's rule. So there may be some confusion with the Cramer's rule. Okay, Cramer's rule. So I will just right now finish that kind of confusion basically. So Cramer's rule, right? What happens was, like, from where this determinant equals 0 came, from here, right? Okay, from here. Okay, now what does Cramer's rule say? Okay, Cramer's rule says that I have equations like this one, a1 b1 c1 a2 b2 c2 a3 b3 and c3. Okay, and this is my variable, right? My unknowns that I need to find, x, y, z. Okay, and at the right hand side this time, right, it is 0. Okay, previously it was d1 d2 d3. So I will write here d1 d2 d3, but in this case, right, in this case my d1 d2 d3 is 0, right? d1 d2 d3 is 0. Now if d1 equals to d2 equals to d3 equals to 0, then, right, then what will be my value, okay, of the determinant of this one for getting a unique solution of xyz. Okay, so what I know is, like, my solution of x I know, right? Like if these are 0, then I hope you remember that my delta 1 equals to delta 2 equals to delta 3 will also be 0. Okay, all of them will be 0. Why? Because when I will find delta 1, I will replace this one with this one, okay, and this is a full rows of zeros, right, rows of zeros. So a rows of zeros will basically make the determinant 0, right? So delta 1, delta 2, all of them will be 0, okay. Just revise Cramer's rule a bit, okay. So what is the problem? The problem is my x1 equals to delta, sorry, not x1, my x equals to delta 1 by delta, right? My x equals to delta 1 by delta. So if delta 1 is like 0, then for any finite value of delta I will always get 0 solution, right? And I don't want that. I want a unique, like, different solution, not zero solution. Zero solution is this v vector only. If this v vector is 0, then I'm getting 0, no worries, okay. If v vector is 0, then I'm getting like 0 equals to 0, that is not an issue, okay. But I want to find this v vector, okay, like this xyz, which is non-zero. So for me to find non-zero solution, what I need basically that this lambda also to be 0. If I get some 0 by 0 format, then I will get some unique solution, right? Some unique solution. That's why, like, you study the Cramer's rule, from there also you will understand that this delta needs to be 0, okay. Delta needs to be 0. Now here, for this case, for this characteristic equation, delta needs to be 0, okay, fine. Delta needs to be 0. But what was the case for, like, the controllability and observability rule? You might say, sir, there the controllability matrix, their delta was not going to 0. It should not be equal to 0, right? So there, this d1, d2, d3 were not equal to 0, right? Why not equal to 0? Okay. So if this d1, d2, d3 are not equal to 0, then if I even replace this column with this one, then my solution will be lambda 1 by delta, right? Now if delta becomes 0, my solution is undefined, right? My solution is undefined, right? So delta can't be 0. Delta has to be some finite value. Delta has to be some finite value, right? Like, not finite, so delta has to be some non-zero value. So if delta is non-zero, then only I will get some unique solution, right? So that is the important thing. There d1, d2, d3 were not 0. Here they are 0. That's why I use this condition to make delta 0, okay. But like, there d1, d2, d3 were some value, right? They were not 0, okay. That's why their delta, basically the determinant of QC, the controllability matrix and the observability matrix, should not be 0, and here they should be 0 to get a unique solution. So I hope that basically clears a bit of doubt basically. So let me write here also for like solution, okay, non-zero solution. This lambda also should be equal to 0, okay. I will get a 0 by 0 format. Now in case of QC and QO, okay, in case of QC and QO, so what is the value in case of QC and QO? So in case of QC and QO, my d1, d2, d3 that I solved, right, during the proof were not equals to 0, okay, not equals to 0, okay. So if they are not equals to 0, then what is happening? Then, right, basically my delta, my again my x will be equals to delta 1 by delta, like delta, and this is not equals to 0, then this has to also not be equals to 0, else I will not get unique solution, okay. So my delta can't be equals to 0, okay. So yeah, this is one thing, okay. So like, then we learned few properties of like eigenvalues and all those things. So one thing I remember, so tell me how many eigenvectors does a identity matrix has, okay. So identity matrix has how many? Whatever the number of order of the matrix is, that number of not eigenvector, eigenvalues, okay. And what are the eigenvalues? Eigenvalues are 1. So identity matrix has only 1 as eigenvalue, but they are repeated, right? They are repeated n times, whatever is the order. And also identity matrix has how many number of eigenvectors? Can you name those? Is it n? No, right? It is not n. Why? It is infinite. because whatever I multiply with identity matrix, I get back my matrix itself, right? So I get back my vector itself. Okay, so my scaling factor is 1 and I get back the same vector. So yeah, that is the main thing, right? So every matrix, okay, is a like an eigenvector to that matrix, right? To identity matrix. So identity matrix has infinite number of eigenvectors. Okay, then basically we studied the concept of diagonalization. Okay, I hope you remember. Okay, so what was the concept of diagonalization? It was basically matrix A equals to this V vector. Like matrix A can be decomposed in terms of this V, D and this V inverse, right? V inverse. Now what is this matrix? D matrix is basically a diagonal matrix in which the diagonal elements are the eigenvalues, right? Are the eigenvalues. And what is this V vector? V vector is basically like columns, okay, a combination of vectors, sorry, eigenvectors, combination of eigenvectors, right? So like what you can write in the V vector, right, is that the first row you can write as the, what do you say, eigenvector corresponding to lambda 1, and the second row you can write eigenvector corresponding to lambda 2. Okay, this you can write like this, you can write. Okay, so yeah, that is it for eigenvector. Okay, now what is my, like, how can I find this diagonalization matrix? Because what we know, this diagonal matrix, right, is very important. Why? Because with the help of diagonal matrix I can simply tell whether the system is controllable or observable, right, from the matrices, right, state space representation. And I told you a few rules also, test also, Gilbert's test, right? So yeah, from there you can identify instantly. This is basically, so that's why diagonalization is very important. That's why I taught you, right? So this is D and this becomes V inverse, this becomes V, right? Okay, this becomes V. Okay, so yeah, this is basically all about the diagonal matrix. Then like we done the, like skipped a few things, then we did the complete solution of state space equations, right? So what was the solution? Tell me. What was xt equals to? Xt equals to phi of what was it, phi of t times x of 0, right? Then what is the order of this one? This is n cross 1. Sorry for yawning, actually it's like 2:30, 3 a.m. at the night, actually, that's why, sorry. Okay, so it may feel like you are also falling asleep. Please don't. Okay, so we are working very hard here. So like this one, right, this one will be Laplace inverse of phi of s b u of s. Okay, so yeah, so what is the order of this one? The order of this one is also n cross 1, right? So this I won't tell. Okay, figure it out for yourself. Why is the order n plus 1? Okay, so this is the state response basically when the input is 0, and this is the state response when the state initial state is 0, right? Initial state is 0. So what is my output? Output is equals to, like, this is also known as the state transition matrix. This can also be written as e raised to power at, right? So this is what I will write. It will be equals to e raised to power at into x of 0, right? E raised to power at into x of 0, okay, times c. Okay, now this is plus c into e raised to power at into b. Like now, right, there is one issue. This is not simple into, this is a convolution. Okay, so what I can write here is without the convolution. So what I will do is simply put this one right there. So Laplace inverse of c into phi of s into b into u of s, right? This is what I will put. And what I will add with this one is plus d of ut. D of ut will just remain outside, so it is not an issue. Okay, we don't do the Laplace inverse because obviously it will be difficult. We do the Laplace inverse at the end, right? So like what is this? This is the zero state response and this is the zero input response. Okay, so yeah, these two things are there. So now what is this phi of t? What is this phi of t? So phi of t, right? Phi of t is the state transition matrix. So I have, it is basically defined as Laplace inverse of Si minus A inverse. Okay, so yeah, this is the Laplace inverse of Si minus A inverse. So what are the few properties you need to keep in mind? One of the few properties is phi of 0 equals to basically identity matrix, and phi k of t, like another property was there, the differentiation of the phi of t, right? So if I have phi dash of t, okay, if I differentiate this becomes A, right? Now what is phi k of t? Phi k of t is basically phi of kt, right? Phi of kt. Now what is phi of t? Like this is also another relation, phi of t1 minus t2, and phi of t2 minus t0 will be simply equals to this phi of t1 minus t0 only. Okay, this is also another property. Just simply put it in terms of explanation and you will see. And one other property is my x of t, right? I can write my state variable in terms of phi of t minus t0 into x of t minus t0, right? So yeah, these are the few properties. So like this one, right? This last one, what does this represent? Remember, right? What does this mean? So I can go from x of t to x of t minus t0, right? So what does this mean? This means I can go from here to here. Also I can come back from here to here, right? To the future and to the past. So this means my state process, right, is a bilateral process. Okay, so yeah, this one was one of the things that we need to remember. Okay, now again the most important formula. Okay, what is the most important formula? It is the transfer function, right? Transfer function. So what is my transfer function? It is basically C into Si minus A B. This is inverse, and this is basically P cross M. So transfer function, right? The order of transfer function will be dependent on the number of outputs and number of inputs, right? So that's why this comes P cross M. And is there anything else? There is, right? There is. And this is D. Now surprisingly, D, what does D has the order? D has order as P cross M, right? P cross M. Okay, so my transfer function is like this one, P cross M. So yeah, this is my transfer function. Now next, what did we study? Yeah, we studied the state space for electrical circuits. Okay, basically what you have to keep in mind, the state variables that we choose. Okay, state variables that we choose is basically and voltage for capacitor. Why so? Because we know, like, it is related with the differentiation, right? So that's why. So C dVc dt equals to IC and L di dt equals to VL. So that's why it's in differentiation, first order differential equation. Okay, voltage, it is responsible for change of the state in system, right? So like my current is dependent on the change in the voltage. So like the voltage will be responsible for changing the current, right? That's why it is responsible for changing the state in the system. Okay, so voltage for capacitor. Now what we did in the similarity transformation part. So similarity transformation, like what is similarity matrices? So for similarity matrices, remember the condition. Is it like same matrix only? No, right? So it was that my eigenvalues should be same. Okay, so my eigenvalues should be same. And what was the another condition for similarity? Are my eigenvectors also should be same? Now if my eigenvectors remain same, then the matrix will be same only, right? So what is the difference? My number of independent eigenvectors should be same, right? Eigenvector will change. Okay, eigenvector will change, but my number of independent eigenvectors on the previous value and this value should be same. So number of okay. So yeah, this is the main thing. So eigenvector may change. Now next, what did we study? So we studied the transfer function decomposition basically. Okay, transfer function decomposition. So like what do you mean by transfer function decomposition, right? So we had four forms, right? One was CCF, next was OCF, next was parallel decomposition, and the fourth one was cascade decomposition. So what does CCF mean? CCF means controllable canonical form. So the decomposition will be always be controllable and it will be canonical. I will choose minimal set of state variables. Okay, that's why. So what we used to do in CCF, right? In CCF, basically, I used to take common the highest power, right, of S from the denominator, and that used to go above, and from there we used to solve, right? So in CCF, what was the key thing to keep in mind? So in CCF, my A will be in standard form. A will be standard form. Standard. My B will be standard. Okay. But my C will depend on numerator. Of transformation. Okay. So my C will depend on numerator of transformation. Okay. So yeah. Now let's take an example. Okay. So how to solve them directly? CCF, right? So my transfer function, let's say my transfer function is this one. Okay, s square d square plus s d1 plus d naught, and in the bottom I have, let's say, s cube plus c2 s square plus c1s plus c naught, right? So this is my transfer function basically. So now what is my A matrix basically? What is my A matrix? So my A matrix, right? A matrix is in this standard form, that my this one will be 0 1 0, this one will be 0 0 1, and the last row, right? Last row, as the order is 3, I will have a 3 cross 3 matrix. Last row I will start from here to here, right? But I will start from here to here in the opposite direction. So what will difference will be, all of them will be negative sign. Okay, you can start from here also, but if you start from here, then the direction will interchange here also. So that is the main thing. So this will be simply minus c naught, this will be minus c1, and this will be minus c2. Okay, minus c naught minus c1. Okay, and minus c2. So yeah, this is basically my transfer function. Now, right, now what will be my B? So B, right, B will be simply standard form 0 0 1 only. Okay, and what will be my C? Basically C will also be like this one. So from C, right, if I move from here to here, again my direction will change. I will move from here to here, and C will always be row matrix, as it is a single output only. Okay, so it is a single output. So I will move from, like, if I move from here to here, then like from right to left, if I move, I will move from left to right, right? And my sign this time will not change, it will remain same. So this will be d0, d1, and d2. So what is d0, d1, d2? I am not telling. These are coefficients. Okay, this is coefficient of s to the power 0, this is coefficient of s to the power 1, all those things, right? I am not explaining it further. I have explained this in the main lecture, right? So what was the thing for OCF? For OCF, right, basically here, right, one thing we have to keep in mind is that the system will always come as controllable, representation will always come as controllable, and here in OCF the representation will always come as observable, right? So for OCF, my A is in standard form, my B isn't, right? B isn't in standard form, but my C is in standard form. And B depends on numerator. Okay, I hope you remember all this, right? So again, now try to remember. Okay, if my transfer function is something like this, that it is d1 of s, I have already done this example. Okay, d1 of s into s cube plus c2 s square plus c1s plus c naught, right? So if my transfer function is this one, then what will be my A matrix? So A matrix will again be standard form, right? A matrix will again be standard form. What will be my A matrix? So A matrix will be simply like, what I will do, I will go from here to here. Okay, from below to above. So here the direction won't change. I will go from below to above. This time I will go the column wise. There I was going row wise. Now I will go column wise. So this is minus c0 minus c1 and minus c2. Now what are the other elements? So here I will start from 1 0 0 and then again 0 1 0. Okay, this is how I will. So this is the standard form for writing A. Now for writing C, right, what will be the standard form? So for writing C it will be 1 0 0. Okay, for writing C. Okay, start from 1 and then go to 0 0. There it was starting from 0 for the B matrix and it was going to 1, right? That is the difference. Now what will my B, right? B will again be same. I am going from, like, let's say from left to right, or let's say from 0 to hero, right? 0 to 1. So from low to high. So here I will go from low to high also. DO D1. Okay, no direction change, no sign change. Here no direction change but sign change. Like here, like there are direction change. I'm going from left to right, so I'll go from right to left, right to left, right. But this case sign change, this case no sign change. Okay, so yeah, these are the things that you need to keep in mind. So then we did basically parallel decomposition. So in parallel decomposition, what we did basically, parallel decomposition, there are two forms. One is diagonal canonical form, another is Jordan canonical form. So when does diagonal canonical form comes into picture? When does it come into picture? It comes into picture when I have distinct eigenvalues, right? If I have distinct eigenvalues, or you might say I have independent eigenvectors, right? So then like this diagonal canonical form comes into the picture. Then I can diagonalize the matrix. Okay, I can diagonalize the transfer function, right? So if I diagonalize the transfer function, I can write it in parallel combination of two transfer functions, right? So for parallel decomposition, what we used to do, I used to apply partial fraction, right? So you apply partial fraction, right? Okay, so this is what I should do. So I have two forms. One is DCF, another is JCF, right? Jordan canonical form. So this one was for independent eigenvectors. So I hope you remember, right? Even though we have independent eigenvectors, the eigenvalues can be same. The scaling factor can be same. Okay, so yeah, and this one is for dependent eigenvectors. Okay, so yeah, this one is this one. So here, like there will be, if they are dependent, right, there will be repeated eigenvalues basically. Okay, and what was the rules basically? So here, right, what will happen is basically I will apply, like, why do we need parallel decomposition? To understand controllability and observability. So with the help of parallel decomposition, I can, just by seeing the matrix or just by seeing the state diagram, I can directly say if it is controllable or observable. Okay, that I will come to. So that's why I need parallel decomposition. And cascade decomposition is nothing, just two transfer functions in cascade. I just multiply one with another one and put a gain of one block before connecting the two integrators, right? That is what a cascade decomposition is. So yeah, that we do. Then comes is the last few topics, that is the controllability. This lecture already went very long. Okay, so what is controllability? Basically, controllability is the ability for my input to control the future state of the system. So means control future state of input with help of with help of input itself, right? So not future state, not future state of input, future state basically of the system, right? Future state of the system of the that is what controllability means. So why do you want to control the state variables? To change the eigenvalues. If I change the eigenvalues, then it will make the system stabilize. It will stabilize the system. So that I want, right? I want to stabilize the system. Okay. So that is what we do. Okay. So yeah. Then the controllability matrix came, right? Controllability Kalman's test. So we can understand controllability, like we can figure out that whether the system is controllable or not with the two methods, right? First one is Kalman's test, and second method is Gilbert's test, right? So what does Kalman say? Kalman gives us one matrix. The proof is not important, okay? The proof that I do is not important. Main outcome is conclusion is important. So with the Kalman's test, what we did was this QC, right? QC, okay? The controllability matrix. What was the controllability matrix? The controllability matrix was like this, right? B, then AB, then A square B, and it went till simply what do you call this a n minus 1 into b, right? Okay, this went till like that. So this is n times, but each b, right? What is b? B is simply n cross 1, right? N cross, not n cross 1, n cross m basically, but like my input is 1 only most of the time, so it is n cross 1. So I have one column but multiple rows, n rows. So this is one column vector, this is a one column vector, and this will go on, right, until I get a square matrix. So this is basically my 2 cross 2 matrix, okay? So not 2 cross 2, sorry, this is n cross n, okay? This will be my n cross n matrix because this is combination of columns. Already we did that, just a bit of revision, okay? So what does Kalman say? Kalman say if my system will be controllable if this determinant of this one is not equal to 0, that is, it is a full rank matrix. Full rank matrix, right? Okay, so this is this one. Now, right, let's solve for the Gilbert's one. So like Gilbert, what does Gilbert say? Like I will not write it here because it's long. Gilbert says that my Jordan block, okay, for repeated eigenvalue, for the same eigenvalue, okay, there should only be one Jordan block, okay? And second, what is the second condition? Second condition is like Jordan block for like the eigenvalues, right? The last row of that for Jordan block for the same eigenvalue, the last row corresponding to that Jordan block corresponding to the B matrix should be non-zero, right? Should be non-zero, okay? So yeah, if you understand, well and good. If you don't, like, go and revise the notes, okay? And yeah, that was basically it. Now, right, this we use in the observability factor also, but before that we learned about bit of pole zero cancellation. So what is pole zero cancellation? Before that, like okay, let me finish the observability, then I will explain the pole zero cancellation. So what does observability mean? So observability means all the state variables are observable to the output. So all the state variables are observable to the output. Again, here the proof is not important, okay? Proof is not important. Okay, so this one is this one. So like here all the state variables are observable to the output. Now what should be my output equals to? So my output, right, output, if my system is observable, my output should be function of all the state variables, right? So then my system will be observable. So again, what does again Kalman came with some rule. So Kalman, right, what does Kalman gave us rule? I solve it differently, people solve it differently. So people, what they do, they find QO is equal to simply this C A transpose C, okay, C transpose, right, and this is A transpose whole square C transpose, and this goes on until this one, right? This goes on until this one. N minus 1 C transpose. Okay, so yeah, this is what my Kalman's test tells us, like the observative matrix. But what I do is I take the transpose of this one, but writing here will be difficult. That's why they don't do it. Okay, but I will do it here. So QOT transpose is equal to simply this. This looks like a column matrix, but this really isn't. This is a combination of rows, right? Yeah, row matrix, combination of row matrix. So this becomes finally n cross n. So this is C only. Okay, this is C transpose, actually C transpose only, and this is, let's say this is CA, this is CA square, and this goes on until C raised to power n minus 1. Okay, C raised to power n minus 1. Okay, so what does this mean? This means that my determinant will be not equal to 0. Okay, determinant will be not equal to 0, like for my system to be observable. So this was basically what Kalman gave. Now what does Gilbert give us? Gilbert, again, there are two rules, one for non-repeated distinct eigenvalues, basically for independent eigenvectors, and another one for repeated, right? So for like non-repeated eigenvalues, again, the column corresponding to the C matrix of each eigenvalues, right, should be non-zero. So each element of the C matrix should be non-zero for non-repeated eigenvalues, right? So C matrix should be non-zero. Okay, each element at least. Okay, if I have now, let's say if I have two rows in C element, so at least one element should be non-zero, right? So yeah, that I explained in that lecture. So I will give you a brief overview. C11, and let's say C12, C22, no, C22. So I have this one, right? So out of this one, so my each eigenvalues will be here. So out of this one, out of these two, only one of them can be 0. Other one has to be non-zero if one of them is 0, right? So like this one also, one of them has to be non-zero. So yeah, this was the Gilbert's test for non-repeated. And for repeated, again, the same first condition is same only. What was the first condition? First condition was that for same eigenvalues I can have only one Jordan block. For the same eigenvalue I can have only one Jordan block. I cannot have more than one Jordan block for the same eigenvalue, right? So in the C matrix, that is important. And what was the second rule? Second rule was for each Jordan block, the first column corresponding to each Jordan block. So let's say this is 2 2 0, or not 0, minus 1. This is 0 0 0. Let's say this is Jordan block, right? Okay, this is Jordan block. So this is Jordan block, right? So the first column corresponding to this Jordan block of the C matrix should be non-zero. Okay, this was the second condition of the Gilbert's test. But if you are confused with the Gilbert's test for repeated eigenvalues, I will highly recommend solve using Kalman's. Okay, so the answer will not come wrong at least. So that is important point. So yeah, I was there in the what pole zero cancellation, right? Pole zero. So what does pole zero means? So if there is some pole zero cancellation, then if there is some pole zero cancellation, it means system either observable or not observable, unobservable or uncontrollable, right? Okay, that is the main thing. So it depends, like whether it will be uncontrollable or unobservable or both. It depends on how I represent the state space. Okay, how I represent the state space equations and how I draw the state space diagram. It depends on that. Okay, so yeah, that was it for the pole zero. Okay, I think, yeah, that is the end of the state space chapter basically. So we'll move on to the next chapter, that is the time response. Okay, so yeah, this chapter went very long, I'm sorry for it. Okay, I hope you found this interesting, because I don't think this type of content is anywhere there. Okay, so I try to understand this state space chapter very well, okay, and then explain it to you. So I hope you understand everything. If you have any doubts, you can like tell in our Telegram group, okay, text there, okay. Thank you.